Okay, good afternoon, everyone. Greetings. Good afternoon. Greetings. Okay, so my name is Keisha Rogers, and I'd like to welcome you here today to the International Schiller Institute. Our event today is in celebration. The Schiller Institute is joining with organizations, NASA, international organizations around the world that are today celebrating the International Observe the Moon Day and also celebrating the World Space Week. This week marks the anniversary of World Space Week, and the theme for World Space Week is very fitting for what we're going to discuss here today, which is the moon, the gateway to the stars. And our title and theme for our event today is really centered around this conception of mankind, humanity as a galactic species. The power of reason lies in the solar system, lies in space. And so we have some excellent speakers for you here today that are going to talk about what is going to be needed to continue to fulfill mankind's extraterrestrial imperative in space, the accomplishments that we've made in space, America being the first nation to go to the moon and land humans on the moon on behalf of all mankind, and how we were able to do that through the engineering and the great breakthroughs and discoveries of some very genius young people, and why we need more young people in the space program today. So what I want to start with is a brief video that came from the lead for Goddard Space Center on International Moon Day. And this young lady's name is Andrea Jones, and she's going to just give us a brief video on the excitement of what's going on around the world for International Observe the Moon Day.
Hello, and welcome to this global celebration of lunar science, exploration, celestial observations, and our personal and cultural connections to the moon. My name is Andrea Jones, and I am the Public Engagement Lead of the Solar System Exploration Division at NASA's Goddard Space Flight Center and the Director of International Observe the Moon Night. This is a very exciting year for the moon. We are celebrating the 50th anniversary of the Apollo moon landing and many more Apollo program anniversaries to come. We have an international fleet of robotic explorers at the moon that are reshaping our understanding of our nearest neighbor in space. And we are looking forward to returning to the moon with NASA's Artemis program, landing the first woman and the next man on the moon by 2024. Right now, we're also celebrating 10 years of International Observe the Moon Night. We are united with people around the world looking up and observing and celebrating the moon together, and I am so glad that you are a part of it. I hope you have a wonderful time connecting with lunar enthusiasts in your community and around the world. Be sure to share your view of the moon or a glimpse into your celebration using the hashtag #ObserveTheMoon on multiple social media platforms, including our Flickr gallery. Find resources that will help you learn more on moon.nasa.gov/observe.
So the Schiller Institute was founded by Helga Zepp-LaRouche, and Helga LaRouche founded the Schiller Institute based on the principles of the Renaissance ideas of mankind, and going back to the European classics, European Renaissance. And part of what we've been doing with the Schiller Institute is the advancement of scientific and cultural breakthroughs throughout the world. And the Schiller Institute, the reason why we're having this event and why we think this is so important is because space exploration is absolutely fundamental to the idea of what differs mankind from the animal, what makes us unique as a species. The Schiller Institute was founded based on the revolutionary ideas of our great republic, of the American Republic, going back to the ideas of Gottfried Leibniz and of Friedrich Schiller, the great German-American poet of freedom. And as a part of our organization, we promote not only breakthroughs in scientific discoveries, the exploration of space, but also on culture, such as the arts and music culture as well. The Schiller Institute has choruses that perform all over the country. And we also are very much using this as the light and gateway for understanding how we alleviate poverty through the advancements of scientific and economic progress. And so today, what you're going to hear in just a moment here is from our founder, Mrs. LaRouche. Let me just tell you that we have an event going on also at the same time as this one, in celebration of this National Space Day, World Space Day, with our National Schiller Institute organization taking place as we speak now in New York City. And so we're actually, this is being, our New York City event is being broadcast all over the world. This event will also be made available to participants as well. And so I want to let you hear from the founder of our organization, Mrs. LaRouche, who's going to talk about why it is that our organization has been founded on this conception that there are no limits to growth, that mankind is a spacefaring extraterrestrial species, that our objective is that we are an extraterrestrial species. We are to explore out into the solar system. There's no such thing as limitations on resources or too many people in the world. And I want you to hear this beautiful remarks from Mrs. LaRouche as she greets us here today.
Hello, I'm very happy to address you, even if it's only by the internet and the video. But it's today a truly joyous day all around the world, and actually above, namely on the ISS, there are celebrations of the International Observe the Moon Day. And all the people who are celebrating have caught a very healthy disease, moon fever. And if you look at it, in only 10 years where this event is celebrated every year, it is now 1,564 events taking place all over the world. In the United States, 526 events. In Europe, 298. India, 268. China, 67. Africa, 27. Latin America, 103. Now, obviously, the number of people who are watching this or are participating in it is in the hundreds of thousands and probably in the millions. And I think I'm not saying too much when I insist that these people are the avant-garde of the future identity of civilization. Because they are understanding that mankind must be united not in a space race for competition, but through cooperation, because this is the only way how you can have a long-term sustainable existence of the human species in space. Now, Nicolaus of Coos, the great thinker who already was mentioned by Dennis earlier, in the 15th century concluded that the only reason why representatives of different nations, cultures, and languages can even communicate with each other is because they all produce great scientists. And I would add especially that they have produced astrophysicists who understand that the future of mankind is for mankind to be a galactic species. Now, let me give you a quote from our collaborator, Kraft Erike, who was a board member of the Schiller Institute until he died, because he described very clearly why space travel and space research is so absolutely important. In the Anthropology of Astronautics, which he wrote in 1957, he wrote, "The concept of space travel carries with it enormous impact because it challenges man on practically all fronts of his physical and spiritual existence. The idea of traveling to other celestial bodies reflects to the highest degree the independence and agility of the human mind. It lends ultimate dignity to man's technical and scientific endeavors. Above all, it touches on the philosophy of his very existence. As a result, the concept of space travel disregards national borders, refuses to recognize differences of historical or ethnological origin, and penetrates the fiber of one sociological and political creed as fast as that of the next. As a technical concept, astronautics is all-embracing and more revolutionary than anything conceived so far, including even atomic technology. As a scientific concept, it is bound to stimulate and rejuvenate practically all fields from astronomy to zoology. Its sociological and political implications are such that future generations may well describe as cautious even the boldest prediction of our time. Now, that unbelievable power of space research and travel should become obvious if you reflect on the fact that the idea that man is leaving the orbit, that man is even leaving Earth and travels to other planets is only 144 years old. And it was first presented in the novel of Jules Verne, From Earth to the Moon. Now, it was a novel, but it had many absolutely accurate predictions which later became true. I would call it much more a vision for the future of mankind than science fiction, because it actually inspired many of the pioneers of space, like Konstantin Tsiolkovsky, who, by the way, has a crater named after him on the far side of the moon, who was a Russian space pioneer, Hermann Oberth, Robert Goddard, and naturally Kraft Erike himself, who was especially standing on the shoulders of Hermann Oberth, but also was extremely inspired by the movie of Fritz Lang, The Woman in the Moon, of 1929. Today, we are very much beyond the novel and beyond the movie. Astronautics has become a scientifically recognized discipline, and only those people who are troglodytes ridicule those who push this, like people ridiculed, or some of the mainstream media ridiculed my husband when he produced in 1987 this marvelous movie, which you should watch, Woman in Mars, which had the beautiful vision of colonizing Mars. Now, today, several countries have moon and Mars projects. You have the US Artemis project, India, China, ESA, the European Space Agency, which actually represents the best of European attitude in these days, and whose Director General, Johann Dietrich Wörner, actually announced Space 4.0 by saying that the International Moon Village, which ESA is planning to build in cooperation, if hopefully with all the other space agencies, will no longer be the preserve of just a few spacefaring nations, but it will be open to all governments, to all private companies, academias, and industry. Now, there are still obviously some obstacles to overcome, but there are promising signs of international cooperation. For example, NASA and the Chinese National Space Administration coordinated efforts around the recent touchdown of the Chang'e 4 Chinese lunar mission, where the moon lander and U-2 basically landed on the far side of the moon. And images of Chang'e 4, the Chang'e 4 landing, were snapped then by NASA's Lunar Reconnaissance Orbiter, and they were released in February of this year. This was clearly a first step in the international cooperation resuming that between the United States and China, which is still hindered a lot by the Wolf Amendment. Now, the leading scientist of China's lunar program, Wu Wai-ren, he actually referred to a request made some years ago at an international conference by NASA, who had asked to, quote, borrow China's Chang'e 4 spacecraft and the Chinese far-side relay satellite in order to plan a mission to the moon's far side. Now, obviously, there is extensive cooperation going on between NASA, Roscosmos, the ESA, the Indian Space Agency, and even with many developing countries who are now cooperating. Now, this is the vision of Kraft Erike and also of, of my husband, Lyndon LaRouche, that basically the moon would be the first colony of this endeavor. As Tsiolkovsky said, it is true that the Earth is the cradle of mankind, but man cannot stay in the cradle forever. The solar system will be our kindergarten. Now, Kraft Erike's vision of the moon city, Selenopolis, is becoming a reality. And Lyndon LaRouche's idea of a Mars colony is now very concretely on the table with Artemis, the Chinese Mars mission in 2000, which will test if it's possible to have terraforming on Mars, in which ESA is also cooperating. There is a model for such a Mars city already in the desert Gobi in China. The beauty of this project is that space projects prove that man is capable of overcoming all seemingly unsurmountable obstacles. Lin, in one of his many beautiful writings about space, asked the question, why should man go to space? Why, many people ask, should we spend all this money for space when there are so many problems on the Earth? Now we have one such representative of this world outlook, Bernie Sanders, who, because of his new Green Deal, wants to solve all problems on Earth first and only then spend the rest for NASA projects. Now this reminds one of Don Quixote fighting windmills, but I cannot see how you can reach Moon or Mars or other planets with windmills as an energy fuel. It is the nature of man to conquer all challenges by exploring the unknown. Kraft Erike referred to the qualitative steps, just to give you an idea that mankind again and again made such steps into the unknown. He describes or refers to Homer, who in the Odyssey describes how Odysseus is actually getting on a ship, not knowing where he would end up. Then, there was obviously the operation by Columbus, which led to the discovery of the New World, where he also did not exactly know where he would end, even so he had maps of Toscanelli and an idea, but it didn't turn out exactly as it was planned. Then think about Yuri Gagarin, the first man actually in space, or think about the Apollo 8 mission. Each time such a qualitative step was made, boundaries were overcome. And with that perspective in mind, it is very clear that even colonies on the Moon and Mars will not be the limit. That they will be only the stepping stones for a new era of discoveries for future cosmic civilizations. Sure, it is clear that space research has a utilitarian value. There's often the quote that every cent spent on the Apollo project brought 14 cents in return in profit. But there are already many manifold benefits of space technology today. For example, agriculture is vastly aided by space technology, space medicine, new materials, the vast resources on other celestial bodies. Think about all the breakthroughs in knowledge about the laws, the fundamental questions of the laws of the universe, which we would not even have an inkling of if we only look with our nose to the ground on the Earth. Lyndon LaRouche wrote in 1986 in his The Science and Technology Needed to Colonize Mars that it was absolutely necessary to go outside the Earth's atmosphere, to go to places like the far side of the Moon or Mars as an indispensable precondition to study the entire spectrum of electromagnetic radiation and the very long to the very, very small waves around all distant stars and galaxies. If we go in this direction, new questions will pose themselves, questions which are not even known today. We will find so-called anomalies where basically they will manifest themselves as disturbing experimental differences with the textbooks. And basically these will all be in combination with astrophysics, microphysics, optical biophysics, and they will produce, every time such an anomaly occurs, they will cause to open the door to new insights about the universe in which we live. This absolutely requires international cooperation. In April this year, the working group of the Event Horizon Telescope published the first images of the immediate environment of the first verified black hole in the galaxy M87. Now, this galaxy is only 55 million light years away from us, and it has only the 6.5 billion time mass of our sun. But with that discovery, the theoretical hypothesis of Albert Einstein's general theory of relativity and the assumption of such black holes was proven more than 100 years later. It did require the international cooperation of many countries around the world, hundreds of scientists who placed 10 radio telescopes in locations around the world, and that span was needed to make this a successful imaging. In the same way, if we build a colony on Mars, which is supposed to be self-sufficient and a long-term endeavor, it will only function if it has the size of a city with hundreds, if not thousands, of scientists and many more people in life-supporting systems. Now, this requires international cooperation. All of this has a deeper anthropological significance. Lyndon LaRouche correctly said that we have to look not only at the span of this present century, but into the next century and several centuries ahead. So man in that time will not be only capable to operate in the solar system, but very likely in the entire galaxies, and maybe even beyond that at some distant future. There is a profound question associated with that about the nature of man. It is very clear that as we have developed as a species from very primitive forms, Stone Age and many steps beyond that, it is very clear that man, by going into space, by developing colonies on other planets, that we will change our identity as mankind. And I'm absolutely optimistic that that will be a very positive change. That through the increase of knowledge about the physical universe, we will also, through the aesthetical education, develop our moral character. So I think that space travel will mean that mankind will, in the not so far distant future, become truly human.
Okay, so we're going to go on to our next speaker here that I will introduce in just a moment here. But, oh, I guess you didn't get the one. Okay, so I'm missing a slide.
But we-
Oops, sorry. Slide there. You will hear from the co-founder of our organization, the husband of Mrs. LaRouche, Lyndon LaRouche, who she spoke about in a little while here after our next speaker, Mr. Cooper, because the question is about visionaries. The way that we actually achieve these goals for getting to space is that you have to have a mission. You have to have a visionary. And President John F. Kennedy was absolutely a visionary before my time, but a visionary that even myself and younger people are continue to be inspired by. In this room today, we even have people who were inspired by the vision of President John F. Kennedy, who worked directly with our space program, who worked directly with achieving the goal of getting a man to the moon and returning him safely to Earth within the decade. And I am happy and honored to be in the presence of such great pioneers of our space program. As Mrs. LaRouche discussed, we had the opportunity with the Schiller Institute to be in the presence of Kraft Erika, who was one of the German-American space pioneers who came over during Pernamanda, during the German space pioneers who came over to work on the American space program. And so the key is that it took courage, it took hard work, and it took people who were determined to carry out the vision of President John F. Kennedy. And today we have another unique opportunity as not only the United States, but nations around the world commit themselves to the return of human presence to the moon. And in order to do this, you actually have to understand you just can't snap your finger, you can't just throw a lot of money at it. It takes some real engineering talent to get there. And so the next speaker that we're going to introduce today to you, and we're delighted to have him here, is Don Cooper. And Mr. Cooper was very much instrumental to the achievement of getting Americans to the moon. And he's a retired physicist. He actually worked out of the Marshall Space Center in Huntsville, Alabama. He was very much instrumental in creating and working with his team and creating the technologies needed to help with the launching of the Apollo mission, the Apollo 11 mission, which I will remind you this year marked the 50th anniversary of the Apollo 11 mission. Just a few months ago, we had an event with the Schiller Institute celebrating the 50th anniversary of man's remarkable achievement of landing the first humans on the moon. And also, Mr. Cooper is going to talk about what his team did to help successfully bring the Apollo 13 crew home safely. A lot of people might remember, some of the younger people specifically have been inspired by the technical accomplishments of the Apollo 13. Some people saw that as a failure because we didn't actually get to the moon with that mission, but that was a massive achievement and a great technical accomplishment. And because of Mr. Cooper's team, we were able to bring that crew home safely, and it paved the way for future missions to continue. And he'll tell us more about that. He's also going to discuss his history and the history of the U.S. rockets and his role in designing the Saturn V ascent guidance and translunar targeting, because you actually have to know what it takes. You just can't guesstimate how you're going to launch the rocket and get into space. You might miss your target, and we don't want to miss our target. So he was spot on with getting us on target to the moon. So without further ado, I would like to welcome Mr. Cooper for his remarks.
By the way, Keisha, we did get to the moon, we just didn't land on the moon. We went around it.
Didn't run around it, right?
In fact,
That's true.
Farther away from the Earth than any other.
That's
mission,
very
except
true.
Apollo 8 was.
But we were headed in the right direction.
Headed in the right direction. That's a good thing. Okay, I'm gonna give you this. Yeah.
And we outdid President Kennedy's mandate by 4-1. We landed 4 men on the moon and brought them back safely in
That's very
1969.
1969.
What I'm going to tell you today, I started about 10 years ago going around to schools and telling the kids how we went to the moon and back. And my objective was to try to inspire them to study math and science. And every once in a while when I get to talk to a physics class, which is fun because I was a physics major, I'll tell them you're in the greatest class you'll ever be in. And if they get through laughing, then I give my presentation. But they don't appreciate it until they get out. In 1961, President John F. Kennedy came to Houston and spoke at Rice University. He said, I believe this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon, returning him safely to the Earth. In July 20th, 1969, we heard these words from the moon, the eagle has landed. In those days, when we thought about rocket history, we thought of 2 men. One was Robert Goddard, which the Goddard Space Flight Center, NASA Center, is named after him. And he was the one that experimented with rockets in the early days. He came up with the idea of using gyroscopes to control the flight. He also came up with liquid propellant, which is liquid hydrogen and oxygen, which we use pretty much today on a lot of rockets. And then after that, Wernher von Braun was born in Germany. You read every paper that Goddard wrote, and von Braun wanted to go to the moon. When von Braun was 22 years old, he was appointed head of the German rocket program. And as some of you know, he designed and built the B-2 rocket. After the Second World War, the U.S. Army realized that we needed expertise in the rocket area, so they went to Germany, Operation Paperclip, and they brought all the German scientists they could find, about 200 of them, to White Sands, New Mexico. They continued their research out there, then they were brought to Huntsville, Alabama. And in 1960, he was appointed head of the Marshall Space Flight Center and given the responsibility to build a Saturn V rocket. This was about 1962. My office in Huntsville overlooked the little airstrip down there, and Kennedy came flying in. And this is President John F. Kennedy right here, shaking hands with Wernher von Braun. And this is Lyndon Johnson right here, standing behind him. That's when they didn't like Johnson. They figured if the plane went down, they didn't care. They just flew them both together.
No, come on.
You younger people probably didn't know that. This is Robert Goddard in the snow up in Maryland. And you can see he's got on his space outfit. And here he's got a rocket about 3 feet long with an elaborate launch stand here. And he's getting ready to send up another experiment.
That's it right there, isn't it? Not?
Yeah.
That same rocket.
That's about it. And,
It's about the size of it.
yeah. And as I tell the kids, you start small, you get bigger, you do more experiments, you get bigger. I was in Florida a few years ago, and lo and behold, I saw the Mercury Redstone sitting at the edge of a parking lot at a restaurant. And there it is, the rocket that put our first astronaut into space. And I made sure that I followed the rules of vacation. You always take a picture of your car. I didn't notice that at first when I got home.
The Russian shuttle was ended up at a restaurant in Moscow.
Really?
Is that right? Something about that. Well, this is, if you ever get a chance to go to Huntsville, Alabama and see the museum there, you'll see a 3-story building right here where there's a Saturn V inside laying on its side like it is at Johnson out here. But beside it is one standing up. You can walk underneath it. It's quite a rocket. These are scale models. This is the Mercury Redstone, and there's the Saturn V. This is the Saturn V with a different nose cone that put our first space station up into Earth orbit. This is the shuttle that went back and forth Earth orbit for years and years. So what is Project Apollo? We're going to lift off from the Earth. We're going to go into orbit around the Earth. Then we're going to do a burn out of Earth orbit called TLI. And notice the latest movie I saw, they didn't know what TLI was, translunar insertion. And we're going to coast 3 days to the moon. We're going to go into orbit around the moon. And then we're going to go down to the surface of the moon, come back up, and then we're going to blast out of lunar orbit. And we're going to coast 3 days back to the Earth, open our parachutes, hopefully land next to an aircraft carrier. The astronauts are going to get on a jet airplane, fly back to Houston, and in 7 days, they left their home in El Lago, or wherever, and made it back to the Earth. So here is Apollo 11 lifting off. You can see here the launch tower is huge, about as big as it is. It's lifting off right here. It has 5 of the largest rocket engines ever built. They produce 1.5 million pounds each, and so there's 5 of them, so you get 7.5 million pounds of thrust, and that's required to lift a vehicle that weighs 6 million pounds when it lifts off. When you think of the size of the Saturn V in length, think of a football field, and you're on the 50-yard line and you're looking at the 2 goal posts. If you laid it down on the football field, it wouldn't fit between those goal posts. A little bit longer than that. These are our first 3 astronauts that went to the moon. We have Neil Armstrong, Buzz Aldrin, and what's his name?
Michael Collins.
The reason why I said that, I actually heard a gal on TV on the anniversary say that.
It's terrible.
Michael Collins. So here's what I tell the kids. If you want to work in any scientific area, whether it be biology, chemistry, physics, it makes no difference what it is. You're not going to get there like this guy just walking around and suddenly ending up on the world's tallest mountain. It's going to be more like this. Robert Goddard, PhD in physics. Werner von Braun, PhD in physics. Neil Armstrong, master's degree in aerospace engineering. Michael Collins, West Point. And Buzz Aldrin, PhD from Massachusetts Institute of Technology. Stay in school, get all the education you can. Education will always give you opportunities. That's why the teachers like it. So, where did we land on Apollo 11? Here's the equator of the moon. And right here next to the equator, right between this mountain range and this mountain range, is a smooth area. And as a matter of fact, when you lift off from the Earth at the Cape and you do the mission planning, you find out that this is the area right here near the equator that requires the least amount of fuel. So we naturally chose some place like this to fly the first mission. The lunar lander has 4 legs. On one of the legs is a plaque. And this is what it says. It still sits on the moon today. Here, man from the planet Earth first set foot upon the moon, July 1969. We came in peace for all mankind. Signed by the 3 astronauts, Richard Nixon, President of the United States. I even made up a joke, when China goes to the moon, they're going to pry this off and sell it on eBay. The kids never laughed. I quit telling them that. They go, what? So here are the Apollo patches. Here's Apollo 7 that went up into Earth orbit and tested out what we call the command module. Here's the service module and the command module here together. And we wanted to make sure that it worked and went around the Earth. And Apollo 8, you can see the symbology, actually went around the moon and came back. Some of y'all may remember that. It was near Christmas when they went on that flight. And then there's Apollo 9, which tested out Rendezvous, which you worked on and knew a lot about. And here is the lunar lander, and there is the service module and command module. And they're practicing Rendezvous, which means get together, separate, come back together, separate, come back together. And you'll see why that's important shortly. And then there's Apollo 10 that did the same kind of testing. And then it was decided it was time to try for the moon. Michael Collins designed this patch. Here's the lunar surface, here's the Earth, and there's an eagle landing on the moon. Well, the astronauts named their vehicles. And Neil Armstrong named the lunar lander the Eagle. So when he radioed back to the moon, the Eagle has landed. We all knew what that meant. And here is Apollo 12, 13, 14, 15, 16, 17. So we have 1, 2, 3, 4, 5, 6, 7. We had 7 attempts to go to the moon and back. 6 of them succeeded. The one that didn't was Apollo 13, which had the explosion, but we got the astronauts back. Here's how we get to orbit. We lift off at time 0. At about a minute after liftoff, we go through maximum dynamic we go through speed of sound. And then we pick up more speed and we have what we call maximum dynamic pressure. And then eventually we go faster and higher until about 12 minutes after liftoff. We achieve a 100-mile circular orbit around the Earth, and we're traveling at about 5 miles per second at that point. And then we reignite our last stage, called the S4B stage, and we burn that to pick up another 10,000 feet per second, and we leave Earth orbit on the way to outer space. And it takes that kind of velocity to get out of the Earth's gravitational field and go somewhere. Go ahead with the lights. And with that, we are now ready to lift off. We can pick up the countdown. Okay, we have some vibration here. The first stage vibrates a lot. I know Buzz Aldrin said one time he had the greatest urge to press the abort button. And it's starting to lift up, and it's going faster. And speed of sound, I'll tell you what I tell the kids also. The astronauts at the top can feel the vibration. They're up here in this little cone. And the sound comes from here, comes up, and they can hear the sound. And once it exceeds the speed of sound, though, then suddenly the sound starts up, but the vehicle just outruns it. That's called Mach 1. And then shortly thereafter, as this vehicle goes faster up through the atmosphere, the air presses down on the top of the vehicle. Just like if you're in your car and you stick your hand out, you can feel the air press on it. If you go faster, it presses harder. And we're all familiar with that. That's called dynamic pressure. And as the rocket goes up, it's the same thing. When it reaches maximum pressure, it's important that the rocket not be rotating. If it is, the pressures are very high and it could break the rocket in half. So designers of ascent guidance make sure it's going straight through the atmosphere at that point. Then it starts tilting over again, heading towards Earth orbit. And the next thing, it runs out of fuel, falls into the Indian Ocean, sinks to the bottom, becomes a home for fish. Environmentally correct. And then we have 5 more rocket engines that are smaller in the second stage, called the S2 stage, and they ignite and they push us higher and faster until we run out of fuel again. Now we have the third stage that has 1 rocket engine, and this pushes us into Earth orbit. So now we're in Earth orbit, circling around. So these things, they always do that. So here we are. This is the Earth. We go into Earth orbit, and we're going to ignite this rocket, and it's going to push us out of Earth orbit, out into space like this. And the moon is over here when we started off. So now, as we go along, the moon is going to move as it goes around the Earth. And remember, this is 3 days. We're going to do our coast out to the moon. And we're going to travel 240,000 miles. I used to ask the kids how far away the moon was. You get a lot of different answers. And so, here we are, and we're right here. We're getting ready to do this burn right here and head out this direction. And at this point in time, way back when I worked for Marshall in Huntsville, Alabama, my boss, who was a woman, George Chandler, called me in and said, Don, we know how we're going to get into Earth orbit, but we don't know what direction we need to be pointed here when we get out of Earth orbit and head towards the moon, so it will end up 10,000 kilometers here right in front of the moon, so we can go into orbit around the moon. So I want you to work on that. I go, wait a minute, I'm only 22. I've already been out of Oklahoma where I grew up. I don't really think about this. Well, it turns out that the first thing I did, I went to the library and I saw one article there by a guy from Jet Propulsion Laboratory on going to Mars. And I thought, well, that's interesting, but it doesn't tell me much. And so I looked everywhere else. I couldn't find anything. I ended up flying out to JPL and talked to him. And he wasn't very enlightening at all. He says, we know how to go to all the planets and outer space, but we never thought about going to the moon. That was such a small job, we never even worked on that. So there was nothing. And so I proceeded to develop a simulation program to do this burn phase and work with Gene Smith that did the guidance here. Gene Smith sat about 8 feet from me, and he'd been working on the guidance for a couple of years. Pencil and paper, of course. We didn't have access to computers very much. We had 2 computers at Marshall, and I got a very high priority. I had 2 minutes a night on the computer to do my simulations. And so I was busily developing software that would coast to the moon and everything, but I still didn't know what direction to go. And one day, this guy named Dr. Hoffner, he worked for von Braun, as a matter of fact, back in Germany. A mathematician, very smart. They had done studies on this, and lo and behold, I was coming down the hall one day, and I saw this picture, and it was kind of like this. It looked better than this, but it was a really nice picture. About as big as that deal there. And the guy was eating potato chips, and I said, what's that? And he says, well, that's going from the Earth to the moon. We've done studies about that. And I said, well, what are all those lines? And he said, well, that's different azimuths. And boy, the light bulb went off. I ran back to my office, and that's when I told Dan Martin. I said, Dan, I know how we're going to get to the moon. All we have to do, this is an ellipsoid. This is the surface. These lines are on the surface of the ellipsoid. All we got to do is get on the surface of that ellipsoid when we cut off, and we'll get to the moon. That's real simple. All we got to do is figure out the mathematics how to do that. But that was nobody else had that idea before. But anyway, so that is how we did the targeting to get to the moon. And
Outgoing asymptote, right, Don?
you're right.
The outgoing asymptote.
Outgoing.
The asymptote
Oh,
of the launch asymptote.
yeah. Well,
That's the way they call it.
really? Okay, we just call it launch asymptote.
Well,
But, so here we are. We left Earth orbit. You won't guess what happens next. This comes out right here. And we open up. This will be like this. And we do our rendezvous maneuver. We turn around and dock with the lunar lander and pull it out of the SLB stage. Just like that. That's something. We're headed, this goes off into space.
or into the moon one time.
I'll talk about that a little bit later. I got that for reserve. So, here we are. We have the lunar lander here, and you can see the 4 legs right here. And we have the command module where the astronauts are right in the middle, and we have the service module with the rocket engine and piston. And we're headed towards the moon. As we get close to the moon, in front of it, this rocket fires and slows us down and puts us into orbit around the moon. Then Buzz Aldrin and Neil Armstrong crawl through the tunnel into the lunar lander, and they separate. And Colin stays here. Yeah, the other guy.
What's his name?
I wasn't going to say that. Colin stays here and stays in orbit around the moon, and our 2 astronauts are here. So now, at the right time, from behind the moon, they ignite this engine, and let me change here to a bigger lunar lander so you can see it better. This is the lunar lander that was printed for me with one of those printers.
Wow, 3D printer?
You see, yeah, you see, here's the descent thing. Yeah, it was done by the kids over at the community college.
HCC.
Down there in Galactic. I'm trying to say, yeah, Missouri City. Stafford, Missouri.
Yeah, great.
And you can see here, here is the, I'm trying to say, here are the 2 windows right here that they look at. And here's the ladder. They walk down to get on the moon. And right here, here's where it separates, right here where I've got my finger. Actually, when it goes back into orbit, it separates and goes back up, and I'll show you that. But anyway, this is the lunar lander. So at the right time from behind the moon, the descent engine ignites, slows them down, and they come out from behind the moon. And when they come out from behind the moon, they're on their back. They're looking straight up at the stars. They can't see the surface of the moon. And they're like this. Aldrin's on the right, Armstrong's on the left. And they're coming down, and this is the lunar surface here. And they're coming like this. And the idea is to kill off their horizontal velocity as fast as they can as they drift towards the moon with the moon's gravity. And then they pitch up and then come straight down and land on all 4 legs. That's the plan. So they come out like this and they pitch up. Armstrong looks out the window and says, "Holy cow, we're headed right towards a crater and some rocks. We can't land there." But now there's a couple of questions. If you were a physics major, you would ask right off, how does he know where that thing's going to land? Where does he know where the guidance equations are going to take him when he pitches up? He's not looking at a computer. Buzz Aldrin is on the right. He's looking at a computer, but he doesn't know. He said, all he said was, when we pitched up and Neil said, "We're along," I said, "What?" I don't know how he knew that, but he was right. They were downrange a little far. Well, on the window that Armstrong's looking out of, guess what? There is what we call crosshairs on the window. And these crosshairs look like this. And I know it's hard to believe for your young people, but we'd invented the joystick for them. And Neil Armstrong had his right hand on it, and what he could do, he could click twice to the left, to the right, and it would change the landing site to there. Well, what he did, he looked beyond the rocks and it was smooth, so he changed the landing site 3 clicks down range and changed the landing site to there. And that told the guy's computer to fly over the rocks and to get back down the other way. Now, he had control of the variation in the descent with his thumb, and so he could control the thrust a little bit. And the idea is to land at less than 5 feet per second, going straight down and making sure you don't tilt and fall up or anything, because you've got to have your launch platform to get back up when you get off the moon. So now we're coming down, and I have here a recording that's primarily Buzz Armstrong talking to Neil on the way down to the moon.
Can you put the speaker on the microphone?
Yeah. Like this? Yeah,
Yeah.
I will. Is that what you mean?
Yes.
Oh, no, backwards. There we What's that trouble? Backwards. Okay, here we go. Okay, right off the bat, 1201 alarm. What in the world was that? Well, what happens is, if the guidance computer on the way down, it looks at the altitude, looks at the velocity, looks at the landing site, controlling the thrust of the engine, and suddenly it has more to do than it can get done in 2 seconds, then it just throws out the answer and starts all over again. Hopes things work out better next time. That's not good. You're right.
But it's doing it every 2 seconds.
Yeah. And but if you can get 8 out of 10 or something like that, you're probably going to be okay. Well, the NASA controller knew that. He had seen that at MIT. Astronauts didn't know about it. Nobody else hardly knew about it. But he said, well, I think we're going to be okay. So, in all his wisdom, sitting here in Houston in his comfortable chair, he says, no problem. Hang tight. Nice mission control there, but you'll hear Buzz Aldrin. Buzz is reading off all the height from the Washington. Now you hear pretty quickly 60 seconds and then 30 seconds. That means seconds of fuel that are left in the lunar lander. And then you'll hear contact light. On 3 of the legs of the lunar lander, there's what are called a probe that hangs down. It's a little over 6 feet long. And when any one of them touches the surface of the moon, the contact light comes on. And what Armstrong does at that point, he immediately presses the button on the control panel which shuts off the descent engine so it will tail off and settle in properly for landing. We finally heard from Armstrong. The only words he said. But there was more conversation that went on. I edited that some, shortened it a little bit. But this is the way it was. And now we're sitting on the surface of the moon. And they get out. Let me find my Here is Buzz Aldrin right here. There's the American flag. This is the lunar lander. This is the first experiment put on the moon. It was a seismic sensing device. And the idea is when the moon vibrates, it's going to pick up the vibrations so geologists can learn about the interior of the moon. Well, why would the moon vibrate? Well, when oil companies do this, they go out and they drill some holes in the ground, they put down dynamite, they blow it up, and causes the earth to vibrate. And they say, well, does that look like there's oil, gas, water, rocks, whatever? And if it looks like it's what they're looking for, oil or gas, they'll say, we'll drill an oil well. Well, I guarantee you they didn't take sticks of dynamite to the moon, and they're not drilling holes either. And so, how do we make the moon vibrate? Well, you remember this guy here that went into outer space? Well, instead of going into outer space after Apollo 12, we just redirected it to the moon and it crashed into the moon and made it vibrate. And then our seismic sensing devices could pick up the vibrations, so the geologists have learned a lot about the interior of the moon.
Where did that land crash?
That was hundreds of miles away from.
Yeah, it didn't land there. that was not the target. This is gives you an idea that this is a mock-up of the lunar lander in Huntsville, Alabama. This guy here climbed over a small fence and made it out there before the guards got him. They just laughed. And here's the door they come out of. They climb down the platform here, down the ladder to get to the moon. And here you can see the 4 legs, the descent engine. Here are the little thrusters up here called RCS, reaction control jets. They're the little 100-pounders that keep this vehicle steady so it doesn't tilt over. There's no atmosphere, so there's no wings or anything like that, so you need that type of thing. Let's see, I think this is, yeah, okay. Now, what we're ready to do, go ahead with the lights. We're ready to go back up, and so here's the lunar lander, and what it does, it comes apart right here. There's another rocket engine at the upper part, comes apart just like this, and leaves 4 legs on the moon. There's the launch pad, and this rocket engine here fires and goes back up into orbit, and so they can rendezvous with Michael Collins. And
It runs by diesel too.
and my words about this are, here they come. Michael Collins.
It runs by diesel too. It runs diesel.
On diesel fuel.
No, not diesel.
For what?
Fuel.
Hypergolic.
Oh, fuel? What kind of fuel?
Hypergolic fuel. Put them together.
Hydrogen, kind of like hydrogen. Yeah, I think it's kind of like kerosene. Hydrogen. And he comes up, and by the power of mathematics, gets to arrives at the right time.
Yeah.
He suddenly becomes very important to these guys. They rendezvous together. They crawl back through the tunnel. They separate. This crashes into the moon. They reignite this engine, pushes them out of lunar orbit. Now they're headed back to Earth. And now, after a while, they determine they're in the right orbit. They don't need the service module anymore. It goes off. And what they're left with is this little command module here that they're in. And they're starting down into the atmosphere. And when they do, they have asbestos here on the bottom to protect them from the heat. They come in upside down, which is normal, just like on the moon, upside down. They come in upside down. And the aircraft carriers down here, the guidance system here is looking where they are, where they're going to go. And now we've suddenly run out of rocket engines. Not quite. We have some little ones right around the edge. And they're able to rotate this thing. And physicists know what that means. That means the center of gravity is going to be offset in the command module. And therefore there's a force vector that's perpendicular as well as longitude. So when they start into the atmosphere, the force vector is pushing on them from the air, but at the right time the guidance computer rotates this vehicle and the force component's this way and it flies like this. And by rotating it back and forth like this, it can fly like this as it's losing velocity and altitude to control the distance that it will fly down to the aircraft carrier. And when it gets down lower, they pop open the parachute, right in the water. We invented frog handle them. They came out, and they opened the hatch, and the 3 astronauts made it back safely. And that's how we went to the moon and back in 1969. About a year later, my phone rang at midnight, and I heard this voice say this. Well, so why would they call some guy that didn't really have any direct thing to do with this other than mathematics years before? Well, it turned out that Johnson had contracted with MIT to write all the guidance equations for the lunar insertion here, the landing, coming back from Earth orbit, the whole thing. And they got a little bit worried that maybe these things might not work correctly. So they needed an independent evaluation. So they went to TRW, who I worked for at the time. Oh, by the way, I did know Poppy Northcutt. I sat right next to her for about 6 months. And people ask me that. That's a really important deal. And so, anyway, for some reason, I never did understand why. They came to me and they wanted me to head up the project. And I said, okay, that sounds good. Sounds like a lot of fun. But there is one thing that I would like you to agree to. And they said, what? And I said, I get to pick the people. So I picked the 15 smartest people that I can move. And tell the kids, that's the secret to project management. Have a whole team smarter than you are. And you'll look good. So we spent almost 3 years evaluating every guidance phase of the Apollo mission for guidance and control. And our conclusions were is that it would work, except for one thing. We did find one problem. When you go into Earth orbit, from the Earth, so this is the orbit, and this is the Earth down here. And we're going to lift off from the Earth, and we're going to go into Earth orbit. We're going to do it with using the least amount of fuel. You would naturally think you fly like this, you come up, and you just kind of ease into the orbit like that. And there you are. You would be wrong. When you do the computer simulations, you find out that the path for minimum fuel is to go a little bit above the orbit, about 3 miles, and come back down into it. And that's the minimum fuel path, as confirmed by calculus variations, and you know mathematics can figure that out. So, when MIT did the descent equations, it's backwards. Here's the moon. Neil Armstrong's up here, and he's coming down. He does 3 clicks down range, which extends the distance. And so the guidance equations have been written such that to minimize the fuel. And so what happens, it determines that the path is slightly below the surface of the moon and come back up right here and land. That's not good. We found that little problem. And we reported it to Johnson. And we waited, and we waited. And 3 months later, we got a reply from MIT. Yeah, we already fixed that problem. I never believed that for a second. But, so I got the call. Of course, one of the things that we studied were all the abort options. When you get to here, and you have an explosion in your service module, and you want to get back to the Earth, what you do is you turn this vehicle around right here, and you fire this engine for about 6 seconds, and what happens is, puts you on, if you get on the right path, you go just like this right back, and you get here the fastest and the quickest from the situation you want to get out of as you have to go. Problem was, there were a lot of problems. The major problems is number one, this vehicle right here is the one that had the explosion. Nobody was going to fire up this engine and take a chance on another explosion, killing all the astronauts. The other possibility was at the other end of this configuration is the descent engine here that we're going to use to land on the moon with, and it's down here at the other end. We could fire this one and slow ourselves down and get back. Trouble is, this is a little bitty rocket engine. It would require about 6 minutes to get back, and not only that, you can appreciate the idea that you have to be pointed in the right direction. And the way you get in the right direction, the astronauts look out the window at the stars and they realign the vehicle and they get it in the right position, and then mission control can tell them what direction they should be pointing to fire this vehicle. All they got to do is hold it on course for 6 minutes, and they come back. The problem with that is the explosion clouded over the window and they couldn't see the stars. I mean, we're going from one problem to another. And they could see the edge of the sun, so they could do approximate alignment. But nobody knew whether that would really work. And the other problem is they're just about at the point to where the moon's gravity is starting to pull harder than the Earth, so they're starting to accelerate towards the moon. That's even a bad situation. That means there's more longer thrust that's needed here. Well, the reason why I got the call is because we had developed a simulation program that would tell us exactly the direction and the length of time to fire this and everything. So they gave us the coordinates, and we ran over to the comp lab. Well, when I got there, there was no car in the parking lot of Building 30. I mean, it was just vacant. I thought it was the wrong place at first. And I'd been there a jillion times. But you walk in the door, there's a guard, and there's a stairway to the right up to mission control on the second floor. And that guard's there to make sure nobody unauthorized goes up the stairs. Well, there was no guard. I just ran up the stairs twice at a time. I was a lot younger in those days, 2 or 3. I ran up the stairs, and I saw the guy in the hallway that had the coordinates. He had it on a piece of paper that he'd pulled out of his pocket somewhere. I mean, real official. He goes, here's the coordinates. Tell us what to do.
Wow.
And so we found the key punch machine. How many of y'all seen the key punch machine? There we go. We got a couple. I have one in my box here somewhere. I'll show the kids. They don't have no clue. And so we found the key punch machine. So Dave McCabe is the guy that did this analysis on the abort. And he was there. So he gets on the key punch machine because he could type and I couldn't type. And he punched out the cards. And I'm standing here holding the cards, looking at them. And I said, I guess I better read them back to you, Dave. It might be good if we don't make a mistake. And so I read the numbers back to him, and so we took them out and we gave them the mission control. They came back again a little bit later and asked for an update. We did that, but it was we didn't know everything was going on, but it was pretty obvious, pretty quick that what were they going to do? They didn't know how much oxygen. They didn't know exactly what to do. They didn't know what the situation was. So what was the decision? The decision was to do nothing. And contrary to the Mars movie, the guy didn't go in the basement with his laptop computer to discover free return trajectories. We already knew about those way before. And the Apollo missions were designed to be free return. What that means is, if you do nothing, the moon's gravity pulls you around the moon, and you come back to the Earth with a perfect re-entry. So that was the decision, and it was about the only decision you could make. Now, of course, that meant the longest path back to Earth and the most time. And in order to survive, they crawled through the tunnel, and they lived in the lunar descent vehicle, which had very thin walls. Since there were 3 of them in here instead of 2, it was too small to put on their spacesuits. They almost froze to death. All of y'all have seen the Apollo 13 movie, saw all the problems that happened on the way back. But they did get back.
But Don, they weren't on a pure free return on 13. They were off free return, and so they did have to do a sizable mid-course to get back.
How many feet?
But they went around.
How many feet per second?
Pardon?
How many feet per second mid-course? Do you know?
Oh, it was small. I'm thinking 20 feet per second or something like that. Maybe even less. I wasn't doing that. I was a rendezvous guy.
Yeah.
So I had nothing to do on that mission. But it did get them back on free return.
Yeah. It was close to it.
Was that slowing them down or speeding them up?
Just corrected the path.
It just corrected the path around the moon.
Oh, I see.
So here's
And
my...
in fact, it threw them further out. It holds the record for the highest altitude, which international records, the aeronautic thing in Paris keeps records. We had to go through and show them that it was X statute miles further than Apollo 8 when it went around the back of the moon. And within 2,000 or 3,000 miles of the same.
So here's my summary of Apollo 13. The astronauts were saved by thousands of nerds. That was the day we became popular. We were invited to parties, and everybody wanted to hear what we had to say. All because we studied math in school.
That's about it.
That actually happened. Somebody invited me to a party and I found out I was the center of attention.
I've got a story on the 1201, 1202 alarm
Okay.
that you might.
Oh,
So let's see, what we'll do before we go to our next speaker here is let's take about 10 minutes of questions. If people have other questions on what Mr. Cooper presented here, shoot, go for it.
I'd like to hear about that 1201 alarm story.
Yeah, I
Yeah.
can do a real short version. I've known Buzz Aldrin since 1964, and he's a smart guy. But it turns out, ironically, and the MIT guys, all of them, I mean, not all of them knew what the real problem was. And it turned out that Buzz had made a late change to the so-called software. We didn't have software, it was firmware. It was wires going through little rings on the computer to quickly improve the switch over to rendezvous radar if you aborted right down to almost landing. And of course, that fuel thing was, it actually ended up 19 seconds with fuel when it landed. And if it had gone below that, they had to abort, come back to the command. Anyway, because of a thing that similarly happened on Apollo 10, our rehearsal mission, where the rendezvous radar suddenly started looking for the CSM instead of looking at the ground or the radar deal. Buzz had MIT put a quick software change in, and it worked, where it would automatically at some point switch to the standby mode for abort, and the rendezvous radar came on. But of course, it was not really looking for the CSM, it was just on, and it was sending data on top of the landing radar data, and that overloaded the, which even that wouldn't have happened in the executive, except some other MIT guys who had actually built the computer, not the software. They built the power supply. They had two phases. One's called phase sequenced or frequency sequences. And depending on how often the computer updated, depending on what program it was in, it started off at 2 seconds update, and that was a different power source, phase sequence on. This is too complex to really explain, and they took all night that night to figure it out. But when it switched to P66 was the descent, automated descent mode. When it switched to that, it went to 1 second updates because, of course, critical within feet to get it right. So when it did that, it had the wrong power setting for the whole computer, and it was being overloaded with this unnecessary rendezvous radar data. And those two alarms, 1201 and 1202, were overload executive alarms. What they were saying is, and all the MIT guys didn't know that. It was saying, hey, we're being overloaded, and they have a priority list, and I was still land. So it was in the right priority. It was just having to throw away all this data, and it was telling them with the alarm, hey, this isn't good to keep doing this. But they just ignored it, and because the guidance guy, a guy named Steve Bays, and he had a backroom guy, he was sitting right next to me, Jack Garman. He knew the computer inside and out. He was telling Steve, tell flight it's okay, they're just executive alarms of overload, just ignore them. And that's what they did.
Thank you.
Yeah,
But,
I was in some flight planning meetings with Buzz for Gemini,
Yeah,
and
me
what,
too.
What little I knew of Buzz, he would tell you right fast. He's the smartest guy in the room,
Oh,
and he's never wrong.
he was never wrong, but he was.
Yeah.
But he's a really good genius about the final phase of rendezvous. But
Yeah.
from the ground up, he didn't.
He
He wasn't
would
the
jump, he would
smartest.
jump to the blackboard and draw out the mission plan. I'd take notes as fast as I could. Boy, I thought, man, he solved all the problems. And somebody leaned over and said, wait till you see it on the computer.
Yeah.
And we'd go back and run the simulations, and it would violate all the tracking station information, you know. And then
Yeah.
we'd have to go back and,
He wanted to do it all on board with silk scarf like all those flyboys did.
what you read about his discoveries in space, what he did with coming to understand the spacewalk.
Oh, yeah, and he
was-
did that on Gemini 12. He
Yeah,
did it great.
phenomenal.
But he really trained for that baby.
Yeah, I'm sure. I'm sure. Okay, well, we want to thank Mr. Cooper for that brilliant presentation. And, you know, so now we understand what it takes to get to the moon. And we need to inspire a new generation of engineers, of scientists to fulfill a new national mission, because this time we're going back to the moon. We're going to the moon not just as one nation, but many nations. We're going to the moon to stay, and it's not just the United States, but we, after the development of those missions where we advance all of the breakthrough technologies, where I'm loud anyway, so I don't know if I need this, but I'll just go ahead. And actually achieve the goal of not only landing on the moon one time, but we did it several times, and we continue to advance and develop our understanding of the breakthrough scientific endeavors needed to get to the moon. And we later on did this, not going to the moon, but we also expanded our exploration into low Earth orbit and did what Kennedy was wanting us to do, which was we started to work internationally. And one of the things that it's going to take for us to get back to the moon is we had the plaque, as he said, we came in peace for all mankind. And at that, prior to the first landing on the moon, what the president had initiated and hoped would happen, but it didn't happen, was that you would actually have a joint mission to the moon with the Soviet Union. And he laid this out as a foundation for achieving peace, to bring about, to stop the threat of war, to stop the threat of mutually assured destruction. But even though we didn't actually go to the moon together with the Russians, with the Soviet Union, later on, what we did do is we started to develop, after the Apollo-Soyuz mission, the partnership in international cooperation in low Earth orbit. And I just wanted to show you this because this is what it's going to take also, you know, for us to think about what it's going to take to get back to the moon. So this is we've sent many crews to the International Space Station, and this is the latest crew on the International Space Station, which is the Expedition 61 crew. As you see, we have 2 women here, 2 American astronauts. One second. You have 2 Russian astronauts. You also have the first ESA, European Space Agency, Italian astronaut, who is the first Italian ESA commander of the ISS mission. So this was a major breakthrough in terms of the diversity, should we say, of those representing the International Space Station. We have almost all of the countries participating, with Europe, the United States, and one day, very soon, when we actually rid of opposition from the U.S. Congress and laws that have been put in place that make no sense, we'll actually be able to have cooperation with the Chinese, which is absolutely essential right now, because as we look at, Mrs. LaRouche talked about this a little bit earlier. I'm not going to go through these, but I just want to go through and show you quickly. This is what China has just accomplished. This is the Chang'e 4 lander on the far side of the moon. As people know, America was the first nation to land human beings on the moon. China has now become the first nation to land a spacecraft on the far side of the moon, and they again, went and made this breakthrough and discovery and for all of mankind, and they're continuing to make new discoveries and new breakthroughs. You also have the Indians, and people look at these two nations and say, wow, there's a lot of people in these nations, there's over 1 billion people, and you have questions of poverty. But the key thing is what India and China have done with their space program is it has been the driver for the ending of poverty in new breakthroughs in science and technology. And just today, just recently, India launched their Chandrayaan-2 mission targeting spacecraft to the moon. And although there were certain technical difficulties with this, what they accomplished with this mission was remarkable scientific and technological feats and breakthroughs. And there was a tweet that actually went out today that I wanted to share based on international cooperation. Here we are. The first mission that actually went to the Indian mission, and remember, the Indians, they're fairly newer in their space program, but they have launched the largest number of payloads. They also have taken several satellites into space, probably more than any other space agency taking satellites in a very short period of time. They launched their first Chandrayaan-1 mission in 2008, and what was just tweeted today by the Australian Space Agency was that with the Chandrayaan-1 mission, the NASA instrument on India's Chandrayaan-1 lunar mission directly observed solid water ice deep in the shadowed craters at the moon's north and south poles. The ice could provide water for future lunar settlements. And this is what we're talking about today. As we talk about getting back to the moon, we're not just going there, for a short-term stay. We're going there for developing permanent presence on the moon. And there are breakthroughs that are being made in cooperation right now, not just for one nation, but the U.S. working with the European Space Agency, working with the ISRO, which is the Indian space program. You have what China's doing right now, China working very closely with the European Space Agency. This is the United States mission that was talked about, that the President of the United States today, President Donald Trump, has called for returning Americans to the moon. And like the other countries, India, also China, there's a very key focus on landing on the lunar South Pole. So think about it. We're going to be, you're going to have India at the lunar South Pole, the United States at the lunar South Pole, you're going to have Russia at the lunar South, everybody there. And So what are we going to do when we get there? We're going to actually say, this is my territory on the lunar South Pole, and that's your territory over there, and you don't come over here on my territory. Or are we actually going to actually go together and say, yeah, howdy neighbor? Exactly. And so that this achievement, this idea that, you know, we're going to, in the United States, we have a plan, a vision to accomplish this goal, to getting the first, actually taking human beings back to the moon, going to the lunar South Pole, this time with the first woman in that process, the first woman to the moon with the Artemis mission. And so it is definitely going to take, and is already starting to take, international cooperation on that. And lastly, before I introduce our next speaker here, what it's going to take is a vision again, and a commitment to a permanent presence on the moon. Earlier, we talked about the collaboration with the great German space pioneer Kraft Erika. This is a schematic, a drawing of Kraft Erika's vision for a lunar settlement on the moon. This is something that's being discussed right now by the European Space Agency, this idea of a moon village. Kraft Erika's lunar settlement was a spectacular idea of a Renaissance city on the moon. And he and Mr. Lyndon LaRouche, who was very much a pioneer and someone who fought very, very strongly for the development of lunar and moon colonization. He even developed a whole program for a 40-year mission to the moon through advanced scientific, technological development, fusion propulsion systems. This is a city that would be powered by nuclear, by fusion power, and this is something that they both were looking at as great visionaries, thinking into the future of, you know, how would you actually sustain human presence for a long duration, both on the moon as a gateway and platform for getting on to Mars. And so our next speaker, before we introduce him, I want to introduce him by first of all playing for you a short clip by Mr. LaRouche, particularly on why the moon is not just a destination. It's not just a place. It's a key for us understanding that, as I said before, there's no reason for poverty on this planet. There's no reason for limitations in growth. That we have the power, have the creative intellect to make the types of discoveries that are needed. The moon is absolutely important for ending wars, for ending poverty, for giving people a mission as we together find a common mission and the common aims of mankind. And so, just give me a second here. I'm sort of, Mike doesn't like this, but that's all right.
I'm pretty sure that was the moon.
Huh?
It was when Kraft Erika and oil came to
Yeah.
nuclear power plants on the moon.
Yes, Selenopolis was on the moon. Yes, that was the moon. That's what it said. Oh, sorry.
But we have to do something else. We have to mobilize the population and its imagination. Because only the desire for a better future, only goals for a better future, can mobilize a population to be motivated to do what has to be done. We have, just when you put this Mars question, we have to industrialize the moon, which is already a project that's understood. 10 nations are actually concerned with the idea of industrializing the moon. 10 nations that are moon landing oriented. We have to take the moon and make the moon a baseline for things going into space. In other words, you don't want to build up tremendous weight in apparatus on Earth and have to pump that stuff up to the moon. What you do is you take your technology to the moon, And then you find the raw materials on the moon, which you use to build the craft. Now you build a craft which will actually take you, or take whatever you want to send, to Mars, that direction. So you have to build an industrialization of the moon. Remember, this is not a new idea. The space pioneers, as early as the immediate post-war period, the 1950s, the United States were already talking about that, as they were in the Soviet Union and elsewhere. The Mars objective was the objective, the planet Mars. Getting there is going to be complicated. It's going to take a lot of science, a lot of development. But that's our mission. We're thinking ahead. We're not thinking about what we're going to get tomorrow. We're thinking about what our people are going to have 2 or 3 generations ahead. And we're thinking about the purpose in life which we're giving to young people today who are coming out of adolescence. The purpose in life for them. When they ask themselves, to what purpose am I living? Am I living to my satisfaction? Am I an animal? Or am I living for the sake of my coming generations? Am I living for the joy of my old age? Am I living to do the things that will give me joy in my old age? They'll take a grandfather will tell his grandson, I helped build that. And here's what you're going to do in your time. Is that force of imagination, when that becomes the policy of nations, to develop the imagination in this way, the scientific imagination, the cultural imagination, where do we want to go? What do we want to promise to our grandchildren and their grandchildren? What do we expect as goals that we think we can realize in this term of life? How do we have to educate our people? What do we have to do now to give a meaning to life? Not the sense, are we animals? Do we just eat and have pleasure from one moment to the other? Or are we people who are thinking about humanity, about future generations, are thinking about what we owe to past generations and what we owe to future generations? Do our lives have meaning? Do they have purpose? Or are we just simply silly pleasure seekers or something, entertainment seekers? And the problem we have today is a cultural problem, which is a moral problem, is that under a zero-growth society, a zero-technological growth society, a greeny society, mankind becomes less than an animal in moral value, where the population requirements that we must anticipate right now is a world level of population of 7 billion. We have to anticipate that now, in this coming generation. And we have to prepare to be able to meet that challenge. And we can. The point is that you make people creative, you inspire them to be creative, inspire them to see objectives beyond what their habits today, and they will be creative, and they will create the ability to satisfy these goals. And mankind is not going to stick around as being just in the nook of this earth, just some corner of the solar system. Mankind is going out into the universe. If we can have a constantly accelerated flight within our galaxy, men in their own lifetime can explore some distant parts of this galaxy. We could do it. So our perspective, we're not going to do this tomorrow, but our perspective has to be in that direction. It's what we have to tell to our children and our grandchildren. This is what we must do. And when you capture the imagination of people in a realistic way, this way, then they become moral, because they become inspired to do good. So therefore, we don't want this nonsense anymore. What we need is high energy flux density power, and high energy flux density is the measurement of effectiveness of production. The higher the energy flux density, and this means you go from incident sunlight, you go up the scale toward nuclear power, and then to thermonuclear power, and beyond that. So the higher the level, for example, if you wanted to take a ship, and you wanted the ship to take you from Earth orbit, that is from the moon, to Mars orbit, with people in it, if you wanted to have that ship travel at a speed which gives you a gravitational effect for the inhabitants of the capsule, you will have a tank attached to you as big as the moon, just to contain the fuel, is not a very good idea. So therefore what you need a much higher energy flux density thing. You need fusion thrust. And where do you get the fusion thrust? Well, you go to the moon. That's your filling station. You'll find at the filling station on the moon there's helium-3, an isotope of helium. Helium-3 is the best fuel from thermonuclear fusion. It's the most efficient. So if you wanted to have a ship so the one gravity effect on the passengers or the crew between Earth orbit and Mars orbit, you would want to have thermonuclear fusion as your propellant. And it would become from helium-3 picked up from the gas station on the moon. And most of the equipment you would fly in would also be built on the moon from raw materials which are present on the moon. And once we get into that racket, we find that we're not limited to the moon. Once we become gatherers of raw materials and so forth in various parts of the solar system, then we find that we have many more kinds of resources to deal with. So in general, the point is we have to go to this kind of development. Therefore, we want a space orientation. We want a power space orientation combined to complement the development of a railway system. Now, in this process, when you start to build a railway system, of the type we're talking about, you're going to have to recreate the machine tool production and so forth that you need. So essentially, in my view, in the United States, what we would do by tradition, we would take a large-scale project, like the Tennessee Valley program, or developing of our railway system, transcontinental railway system. You would take that project and you would assign federal responsibility for creating the credit and authorizing this to build this system. You would then go to private contractors along the way who would pick up on filling out as subcontractors these projects, which is the way things always work in the United States, where they work. And thus, you take a driver, some scientific project, like a space program, a railway program, a water program, building power plants. These things now become the stimulus which spin off the subcontracts and opportunities for expanding industry again. So now we want to increase the productive powers of labor per capita per square kilometer. We take the large projects as drivers. We take the offshoots of the large projects, which are largely national projects, as stimulants for the smaller level, for people who do the things that are necessary to support the larger project out there. Now you can raise the level with aid of education, which is stimulated by this, to increase the productive powers of labor per capita in physical terms. And that's what we used to do in our best time. That's what we did under Roosevelt with a lot of improvisation. Do it again. That's the solution for Asia as well. You have to have the process of self-development of a population through the kinds of goals and stimulants which will enable that to occur in a lawful way. And you have to have a people-carrying orientation. Say, when you've got little kids out there, young people, who have no future, who are extremely poor, with no significant prospect of getting a better life. And this is the way you approach that problem. You transform people who have no future, and you give them a future by creating this process where they are assimilated into the process of the general growth of the society.
Okay, so that's another example of visionary leadership, and although Mr. LaRouche, who was the co-founder of the Schiller Institute, passed away this year in February, actually on Lincoln's birthday, we have to continue that mission. And what he discussed in terms of what is it going to take for us to sustain 7+ billion people on the planet. Well, first of all, if we're going to have 7 billion people on the planet, we cannot eat the babies. We have to have more babies and more creative and productive babies. And we have to sustain them by making sure that we have the appropriate energy systems and that we can expand mankind into the solar system. And that's what Joel Dijon, our next speaker, who has been a long-term collaborator with Mr. LaRouche. I think he joined him and with our Chiller Institute and our organization after finding out about the work of Mr. LaRouche with President Reagan on the Strategic Defense Initiative. And Joel was actually studying electrical engineering. Am I right, Joel?
Yes.
Electrical engineering. And so I'm going to let Joel talk to you about some of the work that he's been doing and what it's going to actually take for us to accomplish this goal for having the type of advanced energy systems that we need. So,
Let's see if I got the mic on.
okay. Can we get his mic turned
hear me?
on? Yeah, okay. Yeah, I think you're good. We'll try it. Let's talk.
Can you hear me?
Yeah, it's not right.
1 second.
It's not coming through the system.
See if we can get that on.
Try again, Joel.
I'm gonna turn this one off.
Testing, 1, 2,
Okay.
okay.
There we go.
I just gotta speak up.
There you go.
Hold on.
1 second. I messed up all the slides, so Mike is gonna come and reset us again.
No, just a second here. Well, we also,
He's resetting the trip wires.
Yeah.
yeah, we're almost tripping on the wires as well. All right, there you go, Joe.
Are you clear?
Yeah.
Okay, before I go to fusion power, I want to go back in time before the Apollo project, before the American Revolution. In 1752, a man in his mid-40s with his son went out in the Philadelphia area during a thunderstorm. And he was a very busy man. I'll go through a little bit of him. And you wouldn't think he would have time to go fly a kite in the middle of a thunderstorm. But I'm sure you all know who I'm talking about. It's Benjamin Franklin. And Mike, can you put up the first slide? Is it up? Okay, that's the younger Ben Franklin, probably younger than the picture on your C-note, or your Benjamin. Now, what was he doing? Well, there was a hypothesis that static electricity, which people in Europe had been experimenting with, and they were using a form of capacitor called a Leyden jar to store electrical charge. They were doing various experiments. And the hypothesis was that lightning had a similar electric charge. Now, Benjamin Franklin, who was born in Massachusetts, and luckily he did not go to Harvard, he was redeployed to Philadelphia, became a printer, and a scientist, an experimenter. So his idea was to take a kite, and the kite, can you see the kite clearly?
Wire.
Okay, you see the wire. Well, it was a silk kite. I don't know if the silk came directly from China, but so there was.
You can see it. It's in the shadow.
Yeah, there was a wire on the top of the kite, and his idea was not to get a direct strike, because if it had hit directly, he wouldn't have survived the experiment. But there was enough charge in the atmosphere that the charge went into the wire, down the rope. He had a key. I don't know if you can see the key.
Yeah.
Key. And he touched the key to see if there was a spark. And then he charged a Leyden jar for future experiments and proved that the electricity in lightning was the same as the static electricity. Now, Franklin was collaborating with some of the top scientists in England and France, all over Europe, and immediately he wrote to George Priestley, who was an English scientist who went on to discover oxygen with Lavoisier from France. And he wrote up his experimental results, and this experiment directly led to further gains of knowledge, so that over the next 100 years after this experiment, we developed the telegraph, eventually the telephone, the electric motor, and it reorganized man's relationship to nature over that 100 year period. Now, Franklin, besides giving us a republic, was known as the new Prometheus. Prometheus, who gave man fire, and was punished for it by Zeus, by the gods. Well, Franklin was considered the new Prometheus, who took lightning from the sky and the scepter from the monarch. So he gave us a republic, and he gave us the American scientific tradition. And I'm going to come back to lightning later on. But what I want to go to now is this idea of fusion. You heard Mr. LaRouche talk about fusion. And by the way, LaRouche is known for emphasizing that the human species is the only species that uses fire. Now, I was watching a nature show the other day on public broadcast, PBS system, and I heard at the beginning that there's a bird in Australia that uses fire.
Oh, yeah.
And I thought, wow, this sounds interesting. So I watched the whole thing. And I don't know if it was Sir Attenborough or one of these British guys, but what happens is that during a lightning storm, lightning strikes the bushes and causes the burning bush, causes a fire. And this bird will go in and pick out a twig and go to a fresh field and drop the trick to spark a fire in the new area to flush out the little animal so he could have a meal. Now, there was no report. I couldn't tell whether the bird actually barbecued these things. But I'm sure that the bird has been doing this for thousands of years and has not changed his MO since it was first discovered. Now, man, like I said, uses fire, uses electrical fire, and over the centuries we've discovered not only chemical fire, electrical fire, but in the early 1900s, beginning of the last century, we discovered the nucleus. We discovered nuclear radiation, nuclear power. Well, I'm going to go through some of the latest developments in fusion research, but just to review. And for those who are concerned, I did find my marbles. So just to give you a little more of a visual, that this is not a marble, this is a proton. I've magnified it 1 quadrillion times, a million billion. And the electron is floating around here somewhere, so keep an eye out for it. So what the sun does, and fusion is the most abundant energy source in the entire universe. All the stars that you see at night, whether they're red dwarfs or supergiant blue giants, they all have at their core a fusion engine. And they have different life cycles, but the most abundant element in the universe is hydrogen. And the nucleus of hydrogen consists of one proton. Now, plasma is the fourth state of nature. You have solid, like this podium, liquid, like your water bottle, gas, like what we're breathing in the room, and plasma is a gas that's heated to such temperatures that the electrons are no longer orbiting a single nucleus, but the electron has been stripped away, so you have a soup of charged particles. The nucleus, which is positively charged, and the electron, which is equal but negative to the positive charged proton. What the sun does, and the sun has the advantage of having a massive gravitational force that can squeeze these protons, because like charges, like if you take your magnet and you try to put together North Pole with North Pole, they repel. And similar to the positive charges, when they come closer together, the force repelling them increases. So you need tremendous heat, you need pressure, and you need containment time in order to force these elements together. Now, the sun has been doing it for 4.5 billion years. Other stars have been doing it, some for longer, some for shorter. But this is not some exotic form of energy. This is what powers the universe. If you look at wind power, solar power, they're all derived from the power from the sun that heats the atmosphere, or the light that powers the solar panels. It all comes from the sun. Now, what LaRouche has emphasized is that instead of having the sun have all the fun, why don't we have a sun on Earth? Why don't we just produce a fusion power for man? Now, it may surprise you to know that we have achieved fusion, thermonuclear fusion on Earth. Matter of fact, 200 years after the kite experiment, in November of 1952, we tested a thermonuclear device using two isotopes of hydrogen, deuterium, which has the proton, but it also has a neutral element called neutron. So it's duo, and another isotope of hydrogen called tritium, which has one proton and two neutrons. And if you use a fission device, you can generate the heat, and with the right configurations, you can fuse the deuterium with the tritium. And the first test of this device produced 1,000 times the power of the fission device. So if you remember the pictures of Hiroshima and the destruction of that atomic device, it was about 14,000 tons of TNT equivalent energy released. The first test of a thermonuclear device released 1,000 times, megatons of equivalent of TNT. Now, the problem is you don't want to release all that energy at once. You want to have a controlled thermonuclear fusion. So that's what we have been working on, both in the United States, in Russia, in China, in Europe, to master the control release of fusion energy. So the first example I want to give you is something called the National Ignition Facility. And can you put that one up? Is it outside?
Yes,
Okay. So this facility is part of the Lawrence Livermore National Laboratory in the Bay Area, in the San Francisco Bay Area. This is a laboratory that was started by Edward Teller, who is known as the father of the hydrogen thermonuclear device. Now, this facility is about 3 football fields. It's even longer than the Saturn V. What this does is it takes a laser pulse and through the various amplifications amplifies it 1 quadrillion times by the time it gets to the target chamber. I want to show you, can you show the target chamber?
Yeah.
You got it?
Yeah, there you
Okay. Okay, so this target chamber is a 10 meter, 33 feet in diameter. Is this the one with the people in it?
Yeah.
Yes.
Okay, so they're not running a test now.
Yeah,
When they
right.
do the test, they evacuate the air, so it's a vacuum. And they place at the center of this chamber a capsule which contains a frozen combination of deuterium and tritium. And the idea is that there are 192 lasers that impinge on the target. I don't know if you can see the target on top of the pedestal, but the target is about the size of an aspirin capsule with the frozen fuel in there. The idea is to apply enough energy to that target so that it will vaporize, but it will compress at the same time. Because you don't want to be like a balloon where you compress and it shoots off in the direction. So you compress it spherically. And the idea is to reach over 100 million degrees centigrade for a long enough time with a dense enough plasma that the elements, the deuterium and the tritium, will fuse. And around the chamber they have various testing apparatus, diagnostic apparatus, so that they've actually measured in various experiments the release of fusion. Now what happens when you have the deuterium and tritium is that, now this will violate the basic math that you may have learned, but when you have tritium, which has 3 nucleons, so you start with tritium, and you put the deuterium, which has 2 nucleons, proton and neutron. So how much is that? That's 5. But not in nuclear physics. Because what happens when they fuse, and again, you need the heat, you need the pressure, and you need the containment time. And when they fuse, instead of having the equivalent of 5 atomic mass units, you end up with 1% less mass than you started out with, a little less than 1%. So that mass becomes energy. And through what Einstein gave us in 1905, the equivalence of energy and mass, that small amount of mass is amplified by 90 quadrillion times to give a huge release of energy. Just for comparison, when you burn methane or you burn, like the space shuttle, when you burn hydrogen molecule and oxygen molecule, you get about 8 electron volts, which is a unit of energy in the very small. When you fuse hydrogen isotopes, like deuterium and tritium, you get 2 million times more energy in electron volts by fusing than you get from just chemical burning. So the energy density is over 1 million times more dense than just chemical reactions. Now, this laser, you can imagine if Ben Franklin were brought to this facility, he would be amazed, because what man has done, and this facility has been operating for about 10 years now, took 10 years to build, and what this facility does is it provides enough energy to the target, the equivalent of over 2 million joules. Now, joules is a form of energy, a unit of energy in much larger than electron volts. To give you a comparison, 1 watt, which is a unit of power, is the energy divided by time in seconds. So 1 watt is 1 joule over 1 second. And if you have a 60-watt light bulb, which is probably illegal now, but if you have a 60-watt light bulb, that's 60 joules in 1 second. Every second, if you keep that on for the whole hour, that's 60 watt hours. And yeah, that's how we measure energy and power. So that laser system applies over 1 million joules to that target. Now, they just discovered, and we're still discovering more about lightning. And I bring this up because they have discovered now that there's something called the superbolt, which is 100 to 1,000 times more powerful than just a regular lightning. And the superbolt is defined as a bolt that has 1 megajoules, 1 million joules of energy. This laser system applies 1 megajoule for 1/1000th of a second, a small amount of time, to that target. So man has recreated lightning in this chamber. Now the idea is to miniaturize this to reach break even, which we have not done yet, where the energy released from the fusion is more than the energy it takes to power up all these lasers and apply it to the target. Now, there's another method of creating fusion, controlled thermonuclear fusion, which is based on using, instead of the lasers and the inertial confinement of your target, use magnetic fields to control both heat, compress, and control the plasma. So I want to go to the next one, the E-Terror.
Oh, well, that's, yeah, okay.
Oh, okay.
That's a few down the line.
Okay, so the next one is.
Keep going, keep going. Yeah, keep going.
Lucky.
Keep going. Keep going. There it is.
Oh, sorry, yep. International.
Okay, yeah. There's an experiment ongoing now. It's being built in southern France called the International Thermonuclear Experimental Reactor. It has 35 nations working on this. US, Russia, China, India, the European Union, I think Iran has been invited. So you have, like I said, almost 3 dozen nations working on this. They're actually building hardware. They intend on having a plasma burn in the mid-20s, say 2025. And their goal is to have 500 megawatts produced with an input of 50 megawatts. So a gain of 10. And they want to produce this for about 10 minutes. So it's not to produce power for the grid. This is an experimental reactor. Now, as you can see, this is a huge device costing billions of dollars. Now, over the last 20 years, there have been a number of companies that have been working on a compact magnetic fusion, where you use magnets that are super cool, superconductors, to increase the magnetic field so you can shrink your device. And one company that is working on a compact magnetic fusion is the largest defense contractor in the US, called Lockheed. And their research division, called the Skunk Works, is actually working on a prototype that would produce about 100 million watts of thermal power. Get that one?
Yeah, there you go.
Okay, so this is instead of a donut like the E-Terror or the Takabak, this is more of a cylinder where you have the coils both around the cylinder and at the ends, and you use radio frequencies to heat the plasma, use the coils to contain the plasma, and the idea is to compress it and heat it for long enough time to produce fusion. Now, this particular design uses like the National Ignition Facility, uses deuterium and tritium, and it's surrounded by a blanket of lithium, which is a blanket that absorbs the high-speed neutrons and converts the energy from the high-speed neutrons to heat, where you could have a heat exchanger running through the lithium blanket and use that to heat, to run turbofans or steam generator, generate electricity. And the advantage of using lithium is that the lithium will absorb some of the neutrons, and after a while it will split and you will get helium and tritium. So you can create new tritium, so you keep that process going. So this is it's been worked on for over 5 years now, and the last video I saw, they promised to have something by the end of this year. So we'll see if they keep their promise. But there's another company called Tri-Alpha. Is that the, or did you get Commonwealth Fusion?
Yeah, I got that one there.
Okay, the Tri-Alpha.
That's it.
That's it. Is that it right there?
Yeah.
Okay, yes.
Okay, Tri-Alpha is a company in Southern California which, instead of using deuterium and tritium, they are using another element called boron. Now, I couldn't fit the boron into this container because boron has 5 protons and 6 neutrons. It's called boron 11. If you've ever used borax, it's got boron in it. Now, boron is a good neutron absorber, but what they do with this system is they have boron and they hit it with a high-speed proton. And what happens is that you have boron 12, it eventually breaks up into 3 alpha particles. Alpha particle being basically the nucleus of helium, helium-4. 2 protons and 2 neutrons. And I don't know if you can see them, but this one has 2 plasmas that are like elliptoids or rugbies. And they shoot them at each other and mix the plasma, and using the high temperature superconductors contain the plasma, and the speed of the collision and the containment will create the fusion. And the advantage of this one is you don't have any neutral products, you don't have any neutrons produced by the reaction. Now, the problem with neutrons is that you can't control them with an electric or magnetic field, and they fly off all over the place, and they eventually damage the sides of your reactor. And if you had something like this in space, you would have to have tremendous shielding to protect your crew, your astronauts. So this company has gotten funding from people like one of the founders of Microsoft, not Bill Gates, the other guy. And a Russian company, so it's had millions of dollars in funding, but it's working on getting this. The problem with the boron is you have to have a higher temperature. Instead of 100 million degrees centigrade, you need 3 billion degrees centigrade. So it's a little tougher to get, but they hope to achieve something in coming years.
Why is it called Norman?
That's the name of one of the inventors who died recently, and they named the upgraded machine after Norman. Now, there's another company in Massachusetts called Commonwealth Fusion Systems. If you could put that one up there.
Keep going. Yep.
Is that it?
Yeah.
Okay.
Okay, now this consists of a group of MIT engineers. And does it show them up there?
Well, they're graphics.
Okay.
Yeah.
But MIT had a high field magnetic confinement system called an Alcator, which was shut down, but this is a company that was spun off of that effort. And they've gotten money from an Italian oil company called ENI. And so they've gotten about $100 million in funding, and they are using high temperature superconductors. Now, a superconductor is just a conductor that at a certain temperature, if you cool it to close to absolute zero, or 4 degrees above absolute zero, there's no resistance in the wires. So being that there's no resistance, you can have tremendous magnetic fields, much stronger magnetic fields than just regular magnets. And they're using a special compound called yttrium barium copper oxide. And they're developing this in the next 3 years so that they can shrink their design to have a smaller compact magnetic reactor that could put out 100 to 200 megawatts of thermal heat. And again, they're still using deuterium and tritium. Now, as LaRouche spoke about in that video clip, we want to go to a higher form of fusion called deuterium helium-3. Now, the advantage of that is that you have the deuterium, and instead of tritium, you use helium-3, which has 2 protons and 1 neutron. And when you fuse those elements, you get, as your product, an alpha particle, or the nucleus of helium, helium-4, which is a charge element, and a proton instead of a neutron. So all the reaction products are charged particles that you can contain with your magnetic field. Now, there's a company that we visited in the Princeton area, near the Princeton Plasma Physics Lab, called the Princeton Fusion Systems, or the Princeton Satellite Systems. And they're working on a design with a smaller power output, about 10 megawatts. But their idea is using deuterium and helium-3, you can actually use the charged reaction products as your thrust. And so you can use it both for power and for thrust. Now, it's not quite ready to produce 1 gravity acceleration, but this would be a step in that direction. Like I said, we visited their offices about 2 years ago, and they produced a 3-minute video clip of their design. And instead of me going through it, I'll let them explain it. And
the direct fusion drive
Yes.
is a new concept in propulsion based on fusion energy, and it provides in a single package both propulsion and electrical power.
So this direct fusion drive is really a game-changing technology, enabling us to reach deep space destinations much faster and with vast amounts of electric power. NASA's interested in a variety of deep space destinations, such as getting to Jupiter in 1 year, Saturn in 2 years, Pluto in 4 to 5 years. A single DFD engine on the smaller side, so a 1 megawatt DFD engine can do any of those missions. We can literally fly straight to Pluto, fly straight to Jupiter, do not stop, do not pass go, do not collect $200, fly directly to your destination. And that's a dramatically different way to operate deep space missions. It will save time, it will save money, and we'll be able to do more science when we get there.
DFD is still under development at the Princeton Plasma Physics Lab.
In DFD, rotating magnetic fields created by antennas on the front and back of the vessel and on top on the bottom create current in the plasma, and that current helps to confine the plasma and to heat the plasma to about 1 billion degrees centigrade. So the purpose of the DFD is to make thrust, but the fusion reactor makes energy, it makes energetic particles, so you have to convert that energy into thrust. We do that by allowing the fusion particles, the fusion products, to pass through the scrape-off layer, heating up the plasma there, and that plasma shoots out the nozzle, generating the thrust.
DFD is different from other fusion concepts because it is much, much smaller.
Ours, which you can see behind here, would be about the size of a minivan.
The current machine, PFRC2, very efficiently heats electrons, and we're upgrading the power supplies so that we can heat ions.
If we can heat the ions in this machine to about 10 million degrees centigrade, we could prove some of the physics theories that have told us we can make a fusion reactor.
A 1 megawatt power plant is ideal for a wide variety of applications. This includes military forward power, remote power, portable power, emergency power, powering mines in the Yukon, and powering spacecraft.
There's a lot of interest in searching for life on Europa, which is one of the moons of Jupiter. We could get there in 1 year with just a single DFT engine.
With a few kilograms of fuel, we'd have enough power for more than 10 years.
We could deflect asteroids that might be coming towards the Earth that would cause major damage. Working on this is very meaningful. The ability to provide power to people on the Earth, the ability to explore the planetary system, to go beyond the planetary system.
We are excited about the future because DFT opens the door to new applications that are not possible today.
But all these engineers were inspired by the Apollo project. And the president of Princeton Plasma, or Princeton Satellite Systems, actually went through with us. He said that he was inspired to go into the space program. So when he went to school, he went to MIT. And when he graduated in '76, there was no space program. I mean, there was a space shuttle that was coming on, and some work, Apollo Soyuz and Skylab, but there was no mission to Mars. There was no mission to go back to the moon. So he went to work on satellite systems. But being that he was near Princeton, he collaborated with the Princeton Plasma Physics Lab, and they came up with this new direct fusion drive system. And again, it hasn't reached break even. It needs additional funding to get to actually having ion heating, and then to be tested on something like the space station, to be tested in space. But we actually conducted an interview. One of my colleagues, Megan Beats, was there with us, and she conducted about a 14-minute interview with Palusak, the president of Plasma Systems. So I wanted to show that. I know there was a lot in that 3-minute, but there's also a lot in this 14-minute interview. The music got better already.
We would have bases on the moon. People would live and work on the moon. We would have colonies on Mars. It'd probably be mostly researchers, but there might be tourist opportunities. It would open up space to the average person. Hi, I'm Mike Palusak. I'm president of Princeton Satellite Systems. We've been in business since 1992. Our focus has been on space and energy technology. We started by working on spacecraft control systems. We started developing software products for spacecraft design and analysis, and then we branched into energy and propulsion. We have been working with the Plasma Physics Lab since 1998 on space propulsion, starting with just plasma propulsion and then moving into nuclear fusion propulsion systems.
And so we were interested in meeting up today specifically on your designs for fusion propulsion. So could you say a little bit about, well, first of all, let me ask you this. Why do we need fusion rockets? Why can't we just continue forever with the chemical propulsion?
The chemical and electric propulsion systems have proven to be great propulsion systems for the missions we've done to date. They got us to the moon. We've done a lot of robotic exploration of Mars, missions all over the solar system, and they've been a spectacular success. The problem is that missions that you might want to do, which require delivering bigger payloads to the outer planets, going into orbit about outer planets, interstellar missions, or sending a lot of people to Mars, really would need better propulsion systems.
And one of the reasons you wrote a paper about is getting people to Mars faster.
Right. One of the things about getting people to Mars is that you would like to get them there faster to minimize damage due to radiation. There may be several different mechanisms in which radiation is bad for astronauts. You want to mitigate that by getting them there faster. That's the simplest way to do it. Alternatives are more shielding and things like that. The other thing about going to Mars with more advanced propulsion systems is you can get yourself away from the launch window problem. For example, if right now with a home and transfer, there are only certain times in which you can go to Mars. With a system that did not require the coast trajectory of a home, and you can get there, you can go there almost any time you want it. This leads to one of the critical things needed is an ability to abort a Mars mission. If your astronauts get sick or the spacecraft develops problems, you want to get back from Mars quickly. And you can do that with a system which has a lot more velocity change capability. And that would imply something which has both reasonably high thrust. We're not talking about like a launch from the Earth. We're talking about 10 to 20 newtons for a spacecraft that humans might be on. And enough power to get them back so you don't have to use a lot of fuel to do that. But that's a critical aspect of any kind of mission to Mars. Look at Apollo 13. They were able to return to Earth. Suppose they couldn't have returned to Earth. They were halfway to Mars. What would have happened then?
Right. So it sounds like you have a lot more degrees of freedom.
Correct.
And then also you had written something on mission to Pluto, or taking the mission to Pluto as an example of the kinds of things the fusion rocket could do.
Yeah, we were very excited about the New Horizons mission, which produced tremendous science. It was a phenomenal technological achievement in a very small package. And it flew by Pluto very quickly and got a lot of data and is sending back to Earth very slowly. Now we thought, well, gee, wouldn't it be much better if we can go into orbit around Pluto? Well, how do you do that? People have proposed fission electric systems. That was done in the early 1990s, a nice NASA paper. And we came up with the idea for a fusion system which would be produce thrust directly from the fusion reaction, not first converting into electricity, and then going to Pluto. It takes about 4 years, then going into orbit, and then using the fusion power plant, switching it to power generation mode to power a lander. So you'd be in orbit around Pluto, you'd be able to send a tremendous amount of data back because you have so much power. More or less the amount of data you can send back is proportional to power. And then you, again, use it for scientific experiments in Pluto orbit and on the surface. Powering the lander was just the idea. It's been thought of, it's like the space powering from the Earth. You just transmit power via a laser beam to, essentially it's a solar array, but you then call it a power array to power the lander. And as you pass over it, you power it, store it up in batteries, and do surface operations and recharge every once in a while.
So could you say something about the fusion rocket that your company has designed?
Right, it's based on an invention by Dr. Samuel Cohen of the Princeton Plasma Physics Lab, which is probably the world's leading center on fusion research. They were the first center, I believe, to generate fusion power from a tokamak back in 1995, the tokamak fusion test reactor. And this machine is different geometry. What it is a closed magnetic donut inside a solenoid. So it's very simple. So you have a solenoidal coil, which is producing a magnetic field, maybe 5 to 7 Tesla. And inside of it, you have a closed magnetic geometry generated by having magnetic fields rotating around, essentially antennas, which cause a plasma current to form. And that's where the fusion happens. Now it's very small, and one reason it has to be small is because the depth of the radio frequency penetration of plasma is limited. So if we had a big machine, we wouldn't be able to heat the whole plasma. So that's one reason to make it small. Another reason is that we want the products of the reaction to leave. Our baseline fuel is deuterium helium-3, which is considered an advanced fuel. That reaction itself does not produce neutrons, but because you have deuterium in the plasma, you're going to get some deuterium side reactions. Those do produce neutrons, and they produce tritium. You really don't want the tritium to fuse, because then you get really high energy neutrons, and you're back to the DT reactor, which has all sorts of material problems. In our machine, it's small enough so that the tritium spirals out and is basically flushed out of the engine, so it does not react. And that gives us a very, very low neutron production and less damage to the reactor, so we hope to be able to get the lifetimes needed to do a mission like to Pluto.
And then it's the charged particles from the reaction and also some deuterium that's inserted that becomes the thrust. Yes,
that's correct. We produce thrust directly. The charged particles leave the reaction. They essentially mix with additional deuterium flowing around the reactor with a scrape-off layer, and that goes out through a magnetic nozzle and generates thrust. And we have to recycle the power that comes out of the reactor due to X-rays and synchrotron and waste heat in order to drive it, because this is the driven reactor. In other words, a driven reactor is one in which the reaction itself does not self-heat. So the products do not give any heat to the reaction, or very little, and we have to drive it, and that's what our rotating magnetic field does. It drives the reaction itself. So we have to recycle it, convert to electricity, and convert it back into RF power.
So how soon can we have a fusion rocket?
Well, we think it would take us between 5 and 7 years to demonstrate fusion. We have not demonstrated it yet. Our current experiment, which is PFRC, Princeton Field Reverse Configuration number 2, has been in operation for a few years. It's getting really good results, but it doesn't have the kind of plasma densities and power levels and temperatures to produce fusion. We want to build another machine, PFRC3, which would actually demonstrate fusion. Now that would be a plasma demonstration. Ideally, in parallel, we would develop all the subsystems so that at the end of the 5 or 7 year period when we demonstrate fusion, we'd then be able to go to a production of at least a terrestrial test bed in a few years after that, and then to a space reactor.
So something in the range of a decade or so.
A decade would be reasonable, yes. I mean, a lot of it is dependent on the funding and how sustained the funding is. And right now we have NASA interested. We have 2 STTR grants from NASA working on subsystems. One is on the radio frequency heating system. The other one is on the magnetic coils. In this case, we're looking at high temperature superconductors, which will make the machine less expensive and hopefully less massive. And then we have a NIAC Phase 2 grant to look at detail and more of the fusion aspects to support the Pluto mission.
Now you mentioned helium-3 as one of the fuel components.
Right.
So when we were speaking before, you said we can get helium-3 through the processing of tritium.
Right.
But there's also a helium-3 source on the moon, an abundant one, and a source in the atmosphere of some of the gas giants. And
That's
so
right.
forth. So can you talk a little bit about that?
Sure. I mean, there was really good work done by the University of Wisconsin showing that it is feasible to mine the moon and bring it back economically. They did an economic analysis. And the technology isn't a whole lot different from what we used on Apollo. We know we can land on the moon and come back. In fact, you can think of the astronauts as being the first helium-3 miners because they did bring back a little bit of helium through in the rocks they brought back. So that's great. So that's one way to do it. The gas giants have enough helium-3 forever. And if you were to develop these fusion-powered rockets, which we're talking about, then it would be practical to go to the gas giants and essentially mine the atmosphere for helium-3. So there'd be essentially unlimited amounts. And once you have this kind of transportation capability, there are lots of things you can do you just couldn't even imagine doing now.
I have 2 more questions for you. One, so your design for a fusion rocket, let's say, is sort of a first-generation fusion rocket.
Yes.
What might the advanced fusion rocket some decades from now look like or be like?
Well, hopefully the specific powers would go up, so you do even more ambitious missions. For example, if you wanted to go to a nearby star system, you need a specific power much, much, much higher than we think we can get now based on our engineering estimates. So that's one thing you would be able to do.
And your company has a paper, an idea of going,
yes,
using that to go to a distant star
That's
system.
right. We actually have the Tennessee Valley Interstellar Workshop coming up. We'll be presenting another paper on it. In fact, our first fusion rocket paper was at the DARPA 100-year Starship Conference, where we talked about going to Alpha Centauri. So, and our idea is not just to fly by, but to go into orbit and say hi to anybody who's there.
So, my last question is, obviously fusion rockets, this is not just an incremental improvement over chemical propulsion. This is a leap to the next level.
Right.
So with that and with the accompanying space infrastructure, like cargo infrastructure and so forth, what could humanity's future look like in a few decades?
Well, remember the movie 2001: A Space Odyssey? It would look pretty much like that. We would have bases on the moon. People would live and work on the moon. We would have colonies on Mars. It'd probably be mostly researchers, but there might be tourist opportunities. It would open up space to the average person because there'd be a lot more opportunities to move places in the solar system. It would be a lot less expensive. So ideas of going on tours around the moon or going to Mars would be feasible. You would have a lot more robotic exploration. We would probably have orbiters around all the gas giants, and these orbiters would have a lot of power. They produce a lot more science. It would be routine. We'd have missions to the 550 AU point where you could use the sun as a gravitational lens to see images of planets in other solar systems at about the resolution as you see the Earth from geo orbit. And you can imagine how exciting that would be to be able to see to that level. And this, we could explore the nearby galaxy doing these things. And we could begin exploration of interstellar space. So all these things would be possible. And it would also make it possible to do things like mine the asteroids and actually make money doing it. Some asteroids with certain metals are economically valuable, and mining them makes sense, but you have to be able to get the materials back at a low cost. And this would allow that to happen. So essentially we'd be really industrializing space, something people have talked about but really hasn't been feasible when you're limited to chemical propulsion and maybe fission, thermal, which is an incremental improvement over chemical that would, future lunar missions, had the Apollo program kept going, would probably have used the nuclear upper stage, fission upper stage, and we tested it, fired them in the desert. But that's again an incremental improvement. So this would open up a lot more possibilities. And with more and more commercial space happening, I think that there's a lot of excitement and people want to get involved in this, and this would broaden their opportunities to get involved in space exploration.
Great. Thanks very much.
Thank you.
So, as you might have caught, he said, what's the holdup? Funding and consistent funding.
Right.
So if we had a crash program modeled on the Apollo project, we could funnel the resources to these various concepts. We don't have to put all our eggs in one basket. But if we have a full court press, we could have break-even fusion in the coming 5 and 10 years, and a usable rocket in the next 15 years. And that would get us to Mars, where the astronauts would actually be able to function instead of being jellyfish when they get there. So that's the potential, and I just want to conclude with one thing. Helga's theme of today's seminar in New York was, we are a galactic species. And if you think back to Ben Franklin's experiment, like I said, we still don't know everything about thunder, and not just lightning in Earth's atmosphere, but now we found lightning in the gas giants. But the dilemma has been, how is the lightning triggered? Because the potential difference between the bottom and the top of the cloud is thought not to be sufficient to cause the strike to actually go ionize the air. And you can think of Ben Franklin as the first plasma physicist. Lightning produces plasma. Well, there's one hypothesis that what triggers the lightning strike is cosmic radiation. High speed, high energy protons and other particles coming from deep beyond our solar system not only influence cloud formation, but also could influence lightning formation. So if you think of that, we could be not only a galactic species, but in control of processes like fusion, and then we can control the weather. We won't have to worry about Greta Thunberg telling us what to do. So I'll leave it there.
Thank you. Yeah, we can take a few questions here.
I do. I don't claim to be a thermodynamic expert, but doesn't this border on defying the 3 laws of thermodynamics?
What, fusion?
Yes.
Well, if you look at
conservation of energy, I mean,
the conversion to
well, the conversion, but it takes, on some of these reactors or whatever you call them, takes as much energy or more than you're producing, doesn't it?
Well, right, we haven't reached break even yet. But the goal of the research, one of the scientists put it like this: it's like you're climbing a mountain and you see the summit, and we've gotten to about halfway up the mountain. We've established the base camp. So we're not starting from scratch. we see the goal, and we know that this is the process that drives the stars. And we know that we can release the energy quickly with thermonuclear bombs. We've detonated enough of those to know that fusion works on Earth.
Right.
But the idea is to control it. So you're right, we haven't gone beyond break even, but we're going up the mountain. And the idea, it's like when Ben Franklin took lightning from the heavens. If you were a peasant plowing the field in Europe, you say, well, big deal, so what? I'm just trying to avoid. But what came out of that? Lightning rods to protect buildings. And by the way, it's now proven that the best lightning rods are in West Texas. Those windmills are excellent for attracting charges from and they don't work too well when they get hit by the lightning. So yes, we haven't reached break even yet, but that's the goal. And if we look at the process, the natural process in the universe, the most common energy source is fusion. So with that, obviously the universe is telling us something.
Right.
Mm-hmm.
So it doesn't violate any of the...
so it can be a perpetual motion machine.
No.
That's the problem. You got to put more energy in than you get out.
Right now, but the goal is to get more out. You see, the problem is the containment.
Right.
You have to contain the plasma, and you have to heat the plasma, and you have to have enough density.
But you need energy to be able to contain the plasma and heat the plasma. So somewhere there is a source that all you're doing is converting it. You're taking back, converting it to your use. But it doesn't violate any entropy laws because somewhere out there, I mean, it's like the fusion in the stars is enabled by the gravitational force.
Exactly.
So you're still getting some energy from somewhere.
But you get a gain. You get more energy out than what you put in.
Yeah, but the energy that you
really
put in
converting.
still got to come from somewhere.
It's an entropy thing. You
No.
got to convert it.
No, because you see, if what you're saying was true, then what Einstein discovered with special relativity would be thrown out the window.
Well, that's what I was getting at. That's really kind of beyond Newtonian physics.
Newtonian physics has been overthrown for over 100 years.
Well, no, not really. Not in everyday life so far, except for thermonuclear devices.
Well, yeah, except for thermonuclear devices.
But
why are we so upset that the North Koreans have thermonuclear?
Oh, I'm not upset. We used them on the moon, on Apollo. We used RTGs.
Right, but those are based on
radiothermal.
The radioactive decay.
Yes.
Right.
It's just another way of converting energy.
Right, but what we're talking about here is that you are taking the smaller elements and you're fusing them, and you get out 1,000,000 times more energy in electron volts than you would if you're just using the chemical bonds, the chemical reaction. And the power, just to give you an idea, the power that the Lawrence Livermore ignition facility uses, they store energy from the grid into capacitor banks. You can almost think of them like the Leyden jars that Franklin was using. And they store that energy and they configure it and they release it in a billionth of a second. So in that billionth of a second, the amount of energy you put on the target is equal to 1,000 times the energy of the entire grid of the United States. So 1,000 terawatts. Now that's just for that billionth of a second. But that we've already proven gives you fusion. The problem is it's only 50 to 70% of the energy that you put into it. The idea is to figure out how to stabilize the plasma so you can contain it. You have the pressure, you have the containment time, and the goal is to get energy gain, a Q above 1.
Thank you very much. Are you saying that the energy that's required to contain the plasma has got to be less than what you get out?
That's the idea, yeah.
Okay, well, but I would still contend that there's something, maybe it's just contained within the space-time continuum somehow, that you're feeding off of to get that extra boost. So in other words, you're taking something out here, you're confining it, and you get an extra boost. But without this out here, you wouldn't get that.
Well, think of your car. You have an ignition, you have a battery. And the idea is that spark that you provide takes energy. So you're taking energy from your battery to provide the spark. But once you get that, as the internal combustion going, it sustains not only enough energy to drive your car, but it recharges your battery so that you're getting a net energy gain.
But you're using solar energy in the form of gas.
Yeah, and where did that solar energy come from?
Possibly. Well, then where that solar energy came from is the gravitational force that caused fusion in the middle of the sun.
All right.
And then,
So,
but then where does the gravitational force come from? You know, you get
What was before the Big Bang?
Well,
your energy is originally coming from the Big Bang somehow.
That's
Where did the Big Bang?
yeah, what was before the Big Bang?
That's right.
But if you think of what we just discovered, Helga LaRouche mentioned this at the beginning, I don't know if you saw it, but this idea of the event horizon of the black hole that was just imaged. Now, we have detected before that, we've detected black holes with this equivalent of 30 to 32 solar masses merging. And we detected this with the gravitational wave detectors. And they estimate that that merger of the 32 solar mass with a 29 solar mass, after the merger, you had a black hole with the equivalent of around 59 or 60 solar masses. So the equivalent of
Good afternoon, everyone.
solar
The library will be closing in 30 minutes. If you need to make arrangements for your ride, please do so at this time. All meeting rooms and study spaces will be closing in 15 minutes.
We can fix this in 30 minutes. The equivalent of 3 solar masses at that instant was more energy than the entire universe put out in that 1 second or less than 1 second merger. So the conversion of mass to energy is where the energy comes from. So you're converting mass, you're multiplying it by 90 quadrillion times. So one atomic mass unit gives you a huge amount of energy. And if you look at matter-antimatter reactions, and we can do this with the colliders, like the Large Hadron Collider, that if you have a proton and an antiproton, and they contact, you get total conversion into energy. And if you go to the hospital today, you take a PET scan, that's using the positrons from a isotope, like fluorine-18 or something. And it interacts with the organs in your body and releases positrons, which collide with the electrons in your body and generates a gamma ray, which can be detected by the detectors. So that if you look at matter-antimatter reactions, you have 100% efficiency in conversion. So where did that energy come from?
Antimatter, anti-gravity, ultimately.
Can I ask a question?
Yes.
And this is a little bit in a different direction. But the idea was, years ago, Lynn was working with a guy named Winston Bostic. I believe he worked out of Florida somewhere.
He was New Jersey Technical Institute. Yeah, at least it was.
But the point is that he was working on this idea of the self-organizing principles within a plasma, which the classical physics said we had to smooth these out, so this self-organization was actually a disruption of the attempt to create the necessary pressures and temperatures inside the plasma. But there was the self-organizing systems is what he was studying. And I just wondered, has anything been going on in that regard that you know of?
Well, part of this field reverse configuration is instead of having this huge donut, that you get the plasma to organize itself. And that's what they are attempting to do with this field reverse, where you generate currents in the plasma that organize the plasma, basically like a smoke ring to contain itself.
Self-contained.
Right. And you heat it, the energy comes from radio frequency energy. But you're putting in radio frequency energy at about 100 kilowatts. And you get out 1 megawatt, like one of the lady who spoke, Stephanie Thomas, is talking about 1 megawatt. So you're putting in 100 kilowatts and you get out 1 megawatt. If you put in 200 kilowatts, you get out 10 megawatts. So it's the magic of the nucleus.
Yeah. Thank you. That's really interesting.
Okay, thank you, Joel.
Yes, thank you, Joel.
Excellent, thank you so much. And I just have a couple of, closing remarks and announcements here, basically closing announcements real quick, is to tell you all that first of all, as we said earlier today, this evening is International Observe the Moon Night, so people across the world are going to be looking up at the moon. And you know, as you go out, I would invite you, here's a little invite here. We're going to go, some of us out tonight. Everyone's welcome to join us over to what the Lunar Planetary Institute is doing right down the street here, Bay Area Boulevard. They're having from 7 to 9, Observe the Moon Night. Think about, as you're looking up at the moon tonight, seeing up there lunar cities on the moon, fusion-powered rockets and nuclear freighters. You're thinking about colonies of people on the moon from all different nations, from all different backgrounds. So, you know, you should be inspired tonight to really look up and see a great vision. So I invite you to do that. Also, before we leave here today, I'd like for all of you to help me today to wish someone very special a happy birthday. My husband Ian, Mr. Matt. We want to wish Ian a stellar birthday.
All right.
And we're going to be going out. Everyone's invited to come and join us. We're going to be going for